Today we are going inside the most critical zone of the blast furnace, the hearth. Our focus is on a single invisible line that determines the integrity and longevity of the entire vessel, the 1150 degrees Celsius isotherm. Understanding this is not just academic, it is the difference between a stable campaign and a catastrophic failure. Think of this as a front line in the battle to protect our furnace. Let's establish the fundamentals. On one side, we have our carbon lining thickness, a direct measure of our remaining defense. On the other, the location of 1150 isotherm, the leading indicator of the degradation. Above this line, iron is liquid, corrosive, and actively attacking the brickwork. Below it, iron is solid, forming a protection skull that shield the carbon. Our primary operational goal is to keep this isotherm buried deep within the lining, away from the final barrier. So, how do we track an invisible line? With our eyes on the inside thermocouples strategically embedded in the shell and brickwork. These sensors provide a real-time thermal map. We are not just looking at individual temperature, we are interpreting a thermal gradient. When shell temperature rises, it's a direct signal that 1150 isotherm is migrating outward towards us. This is our earliest warning system. To understand the defense, you must know the enemy's weapon. Here is the core of the problem: carbon dissolution. The molten iron saturated with the carbon is constantly trying to dissolve our carbon brick back into itself. The 1150 isotherm represents the phase change frontier where this dissolution halt. The space between this isotherm and the molten iron bath is where the erosion is actively occurring. Our carbon lining is being consumed in this zone. The position of this critical isotherm is not static. It is dynamic equilibrium influenced by two main categories of factors. The first, furnace geometry and operating conditions. The hearth shape, the type of fuel, and the overall operating intensity. And secondly, the material properties and our monitoring strategy, the thermal conductivity of the brick and the precise placement of our thermocouple. Controlling this variable is how we manage this line. This is the reality of the fight. On one side, we have the enemy, molten iron at 1500 degrees Celsius or more, incredibly corrode, and it has a relentless corrosion. On the other, our defense, the carbon brick lining. The mission is absolute. Protect the steel shell at all costs. A breakout where molten iron breaches the shell is not an operational incident. It is a catastrophic failure. It's not an option. Why 1150 degrees Celsius? This is not an arbitrary number. This is a metallurgical science. This is the freezing point of iron, the liquidus point for the typical carbon saturated iron in the hearth. Above it, iron is liquid and corrosive. Below it, iron is solid and protective. So, this magical number is the definitive boundary between an corrosive and erosive environment and a protective one. It's the most important temperature in the hearth management. Though our thermocouples network, we can visualize this invisible line. These sensors allow us to plot the contour of the 1150 isotherm. And this contour is not just a temperature line, it is the exact profile of our remaining lining. It is the erosion front. By mapping it, we move from guessing about refractive year to knowing with precision the true shape, the thickness of our defense. Now, what are you really looking at on the monitoring screen? Don't just see numbers, interpret the narrative. For example, if a thermocouple read 1180, we use thermal models to calculate that 1150 line is, say, 50 millimeter behind it. From the original brick thickness, we can deduce we have approximately 800 millimeters of sound lining left. A stable or slowly moving inward line is good. A steady outward movement is a major red flag. It signals active ongoing erosion. This data gives us a predictive power for maintenance planning and is our primary tool for preventing a breakout. So operator, you are the guardians of this line. In conclusion, the effective hearth management is a continuous cycle. It starts with the training our operators to be expert interpreters of this data. We then use the data to refine our thermal models, calibrate our instrument for absolute accuracy, and validate finding against other operational indicators. The 1150 isotherm is our guide. Monitor its movement and understand its meaning and use that knowledge to defend the heart of the hearth.